I will start with the first one. As I said, it's the first step of understanding digital fabrication with concrete. And it's my pleasure to introduce Dr. Jacques Kruger, that he will present the science behind digital fabrication with concrete. Jacques Kruger is currently the Concrete and Structures Laboratory Manager at Stellenbosch University in South Africa, and he simultaneously performs postdoctoral research in 3D concrete printing and digital fabrication with concrete. He recently developed some real mechanical models to quantify constructability performance of 3D concrete printing. It's really my pleasure to introduce him with a virtual applause. So thank you, Jacques, and good luck.
Thank you very much, Constantino. It's a great honor for me to form part of this group, and I really hope to add a lot of value where I can. So I'll be speaking about the science behind digital fabrication with concrete. It's more to do with the material and constructability design aspects. So that is in terms of the fresh state material and how do you actually print something. So the first question I get from people that see 3D concrete printing for the first time is, how do you print concrete? You know, this is not a material that you usually, it's usually a plastic like ABS or PLA, etc. So people typically think of concrete as a very stiff material with large aggregates, and it's difficult to place. So number one, how do you print it? And then secondly, how do you stack all these layers on top of each other without the product falling over, all right? So the answer to both of those questions is thixotropy material behavior. I'll elaborate on that a bit later. But in this picture, you can see a 3-meter column printed by Ghent University of Technology. So this was in 11 minutes. This is not just a new record, it's a world record. I don't know of anybody that can beat this. So they attained a vertical building rate of 0.27 meters per minute. This is extremely fast and likely it's not always needed when you print larger scale elements. So if you go to load bearing structures, say for instance, houses and etc., then you won't need this fast vertical building rate. So thixotropy is really at the center of all of this. So to give you an example, at Stellenbosch University, we conduct a lot of buildability tests, which essentially is just printing a lot of filament layers on top of each other until the column falls over. So it's either plastic yielding or elastic buckling, just like a typical structural design. So in our case, we printed a hollow column, 250 mil diameter, lay height 10 mil speed, printing speed 60 millimeters per second. And in 14 minutes, we attained 670 millimeters of height, and then it collapsed by plastic yielding. So this was a reference mix, and we achieved 0.05 meters per minute vertical building rate. Now, compared to Ghent University, that's about 5 times less, but still it's not bad because we didn't use any accelerator, right? So to further prove this point, we added to our reference mix 2% nano silica carbide particles, okay? And essentially what this does is just improves the thixotropy behavior and allows you to either print taller, as you can see, so we got about 300 mils extra in height, or you can print faster. It's really up to you what you want to achieve. So this is done just with thixotropy material behavior and no accelerator whatsoever. So the question, what is thixotropy? So this is an advanced rheological material behavior, and it's not widely known. So just a brief overview, if you look at this graph on the left. So essentially it's an interconnected particle structure, right? There's intermolecular forces, typically van der Waals forces that attract particles to each other. So if this resembles a materials microstructure, you start on the left-hand side, okay? So you have a network formed, it's completely structured, right? So you have elastic response and in its resting phase, okay? If you add any type of shearing agitation, so if that's pumping or manual mixing or whatever the case may be, you get shear thinning, right? So the interlayer or the interforces between the particles are broken down. If you continue with the shearing, then you get this completely unstructured microstructure. So this is a viscous response. So it's more like a fluid when it flows. Now, if you leave this material to rest, to stand, no more force imparted on it, so no more pumping or mixing, then you get this restructuration or actually reflocculation starting to happen. So it's partially structured. So you get this viscoelastic response. And if you leave it long enough, you get this original microstructure again, which is the elastic response. So this essentially is what we need to get good 3D printing, okay? So to put it into context, we characterize this with the use of the I-choriometer. So there are various different rheometers that you can use, and we apply a constant shear rate. So which means you have a constant angular velocity on the vane, and you get the shear stress as a function of time response. So first, at the first peak or the only peak, you get the static yield shear stress, right? Which is essentially the yield stress in normal material science terms. Then you get the dynamic yield shear stress, which is the force or stress required to maintain constant flow, okay? So when you go from the static to the dynamic yield shear stress, you get deflocculation. If you look at this graph on the left-hand side, essentially this top of this figure. When you remove the agitation while at this dynamic yield shear stress, so when you stop, say, the rheometer's vane, or you stop the pumping, then it reflocculates back to the static yield shear stress, as you can see in the bottom half of this figure, to get the original microstructure back again, so the elastic response. All right, so the dynamic yield shear stress is good for pumping, and the static yield shear stress is to attain the buildability. So in context of 3D concrete printing or digital fabrication with concrete, thixotropy would be as follows. When you place, and this is our example, our printer that we designed and manufactured at Stellenbosch University. So if you place the concrete into the hopper and you start pumping it, then you get the deflocculation, all right? So all the way through those, it follows those to the nozzle, it deflocculates. So when it exits the nozzle, it's mostly deflocculated. It depends if the shear flow or plug flow, but it gets very complicated. So let's just assume that it is completely deflocculated when it exits the nozzle. When you place it, so the first layer, then it reflocculates, all right? And essentially then you retain or you get your static yield shear stress back, which allows you to get the buildability. So that is to place all the layers on top of each other. And that is essentially the thixotropic behavior for 3D concrete printing. Now, in terms of how we quantify this, I developed this model as part of my PhD, which just essentially summarizes what I said, where you start with your dynamic yield shear stress, and it reflocculates all the way to the static yield shear stress, and then it's structure H, which is commonly referred to as A-thix, and that is influenced by amongst many other things, but also by the accelerator. So if you have a concrete that sets very fast, your A-thix will typically be much steeper, and also vice versa. So why is thixotropy important? So you should already know the first one, pumpability, obviously, but also extrudability, which is just a consequence of pumpability. And if you look at this, this is a prime example of what you do not want to achieve, all right? So this is not a thixotropy material. It's terrible, but it's a good photo to illustrate what you do not want to get. So then you also want filament shape retention. So this is basically as soon as you deposit the filament onto the board or onto a previous filament, then you have the original undeformed layer, and under its own self-weight, you get this deformed sort of shape. And if it deforms too much, you will lose your aesthetics. So you really don't want a lot of deformation, especially not plastic yielding under its own weight. And then obviously you want to build these layers on top of each other, and which is buildability. And then you can quantify this in terms of the vertical building rate. And then in this case, you can see it just fell over with plastic yielding on the bottom left side. All right, so the thixotropy really is important for the entire cycle of 3D printing, from the material pumping all the way to getting the object out. So together with constructability optimization, which I'll speak about now, it enables us to avoid using chemical accelerators, right? So this is not something we really want to use if we can avoid it. So why is this the case? Well, if you look at this graph on the left-hand side, this is by Lair et al. They performed on a printable material direct tensile tests. Okay, so this green arrow is cast specimen, where they got a bond strength or say a tensile strength about 3 MPa. Now for printed samples, which starts at 0 and all the way to the right, because that's the printing time gap between the deposition of the successive filament layers. So if you can keep that close to 0, the tensile strength reduces to about 2.2 MPa. So that's already quite a lot less. And this is all just due to the interlayer. And if you wait 1 hour between deposition, it reduces to 1.5, right? So that's half of the cast specimen's tensile strength. So if you just follow this mean strength curve all the way down, you can see at 7 days there's virtually nothing left. So it's really something that we need to look at because it causes severe anisotropy. So further, it also affects durability. This was a structure also printed, I think it was from Narela, yes, where they poured water into that, and you can actually see the water seeping through the interlayers, right? And this is not favorable, especially if you think about including reinforcement into the process, because you'll obviously then, there will be the potential to accelerate the corrosion rate. So the interlayer bond strength is similar to the conventional cold joint formation that we all know. Accelerating agent enhances hydration, so it speeds up the hardening and reducing the setting time, okay? So weaker interlayer bond strength is obtained at shorter pass times. And this is essentially why we do not want to use an accelerator, because for instance, if we look at the 1 hour printing time gap, if you get 1.5 MPa at 1 hour printing time gap and you add accelerator, it could actually reduce to say 30 minutes where you attain 1.5 MPa bond strength. So that is the prime reason why we do not really want to use an accelerating agent. So just to move further, Constantino already showed a picture of something similar, but this is all the test directions that you can test for due to the interlayers and the orientations. But typically orientation 3 is the weakest because you have the normal stress perpendicular to your interlayers, which is essentially then the tensile strength. So it causes severe anisotropy, but we can address that. Then on the top right hand side, it's a study that we did at Stellenbosch University on the fire performance of 3D printed concrete. So for high performance material, we casted the sample and then we heated it up with radiant panels. And at just about 120 degrees Celsius, the high performance concrete exploded. So it's thermal hygral spalling. It's quite explosive. There's nothing left and we lost all our equipment. But nonetheless, it didn't happen for the concrete specimens, where you can see it just delaminated on the interlayer for every specimen. So although its fire performance is better, it still delaminates under its own weight. So it's something we should also address. And then on the bottom right-hand side, you can see you get that's micro XRF mapping of chlorides, where the chlorides just migrate through the interlayers. Obviously, again, it's not something that you want to see if you want to include steel into your 3D printed concrete. So constructability optimization, what is the objective? So we want to keep the pass time as short as possible. Okay, so this is so that we can get better interlayer bond strength, right? Whilst avoiding structural failure during printing. So this is either due to plastic yielding or to elastic buckling. So if you want to print, for instance, a wall element like this, that is 1 meter tall, then you don't just want to reach 800 millimeters, you want to get 1 meter, right? So I will present an example of how you can actually design for this in the fresh state to get better hardened state or mechanical properties. So let's take that wall as an example. This is typically, obviously, you'll design this on AutoCAD. So you have the plan dimensions, and in our case, we want this wall 500 millimeters tall. Second step would be to characterize your material. So I used a model that I developed also as part of my PhD, and it uses the material characterization in terms of rheology and not the green state mechanical strength. So you characterize your material to get the material input parameters. Your geometric input parameters is typically your width of the filament layer, your print path length. So this is 2.4 meters, and this is essentially if you take the line length of one filament layer of each basically Z layer. So that's 2.4 meters. Design height, 500 mils, that's what we want to attain. We won't settle for less. So feasible print parameter range, and this is really where we start to iterate to see what we can achieve, okay? So we first look at the layer height. We use a circular nozzle, so realistically we can only go down as low as 8 millimeter layer height or 15, because if you go larger than 15, you get the rounded layer and it really doesn't actually perform well buildability wise or aesthetic. So then for your print speed, 40 to 100 mils per second. This is also printer dependent. So it's obviously if your motors are strong enough or if the vibrations aren't excessive, etc. Right? And what is interesting, if you look at this equation on the right, this is your predicted vertical building rate. Then you have 3 parameters, of which the 2 ones we just mentioned are the ones that you can change because you don't want to change the geometry of your object. Okay. So what we do, we use a model. So my model only accounts for plastic yielding, but there are other models that you can use for material characterization or just for the model itself, the mechanics. A good model would be Akasaker from TUE, which also accounts for elastic buckling, right? So what do we get? We get the design envelope on your left-hand side over here. Okay, so on the y-axis, you have the vertical building rate, which we want to obviously get the highest as possible. The x-axis, we have the print speed. And in the legend, we have the filament layer heights all the way from as small as 4 mils to 24. In fact, there was more, but I just kept it to 24. So all the combinations that you can see, the colored dots in here, this is what you can use, and you will achieve 500 mils height, okay? If you, for some reason, want a combination that's anywhere above these colored dots, then failure will occur, okay? So you won't achieve the 500 mils that you specified. However, if you are below these, then you get infinite printing as your materials hardening or hydration kinetics and the vertical building rate doesn't coincide. So you can virtually print forever. So, but in our case, obviously, we want to get the fastest vertical building rate. So if you look on the right-hand side, we now apply our constraints. So we have the 40 mil printing speed and the 100, and then the 8 to about 12 filament layer height. And then you get this triangle. Okay, so we want the most top point, so it will be that blue one over there, which essentially gives you a print speed of 87 millimeters per second and a filament layer height of 8 mils. Right, so now you can check what is your pass time. So you take your path length divided by your speed, which is 27 seconds, and essentially that is 0. Right, it's so small, you can take it as 0. Now you do your checks and you see, okay, interlayer bond strength. So you'll have to characterize for your own material how the interlayer bond strength reduces with your printing time gap, and say it's, in our case, almost 0. Yes, that's fine. You can go on and check your mechanical strength, durability, fire performance, etc., etc. Right? So if it's not okay, you first start by improving your material yield stresses and thixotropy. That is the absolute first step that you should do. The second step, try some other solutions. So improvise, engineer, research, anything else that you can think of. Because the third step is not what you really want to do, but if you have no choice, then you should obviously do it. So alter the object geometry, we don't want to do that. Or use accelerating agents. Again, if you add too much, you can really bring that all the way down, and for load-bearing structures, that will have a lot of consequences. So that's really the last resort to add chemical accelerators. So if it's okay, then happy printing. As an example, I think it was a year or 2 ago, we did an X-bench project with two of our PhD students. We printed this bench. I think it's about 1 meter in length. And we applied a load with our Instron actuator on this transfer beam. And surprisingly, for a thin-walled concrete element, I think it's about 30 or 40 mils thick, this bench could sustain a load of 3 tons, where we didn't even get brittle failure because we added polyprop fibers. So it was just starting to crack. So if you design correctly, you can really get strong structures, even though you have interlayers. So takeaways. The first one, fresh concrete state properties and print parameters for 3D PC influence hardened concrete state performance. So this is really the first one that we should know for 3D concrete printing, is that the design process in the fresh state will influence your hardened state performance as well. But number two, we can account for it via thixotropy and the optimization process. And lastly, only use chemical accelerators when absolutely necessary. So that is it from my side. I hope you guys enjoyed it and learned something. Feel free to email me. My email is here at the bottom, and enjoy the rest of the presentations.
Thank you very much, Jacques. Thank you very much. Really interesting presentation. So I agree with you that the fresh state in concrete printing is a very complex situation. So it needs to be addressed very carefully. And you have provided a good overview on how the technology is, so how the rheology is affected by the technology. So we have collected many questions, and I will be glad to give it to you some interesting questions that have arisen from the